We can learn a lot about the galaxy we live in and the larger universe by observing the motions of astronomical objects. Now, we can't watch these things move in real time. Although their motions are rapid, the timescales we have access to are too small. Rather, we measure their instantaneous velocity and piece together the sense of their motions over cosmic time. They're a series of nested motions, making you wonder exactly what is at rest. The Earth spins on its axis and has an annual orbit of the Sun. The Sun has a motion with respect to the stars nearby, and the entire set of nearby stars are being carried around a long circular orbit of the Milky Way disk. The Milky Way, as an entire galaxy, is indulging in motion towards the Andromeda Galaxy, and the pair of galaxies plus a few dozen dwarfs are moving with respect to a much larger cluster called the Virgo cluster. Presumably, on the largest possible scales, the universe itself is not moving, and astronomers have been able to recover an inertial frame, or a large set of galaxies which have no net motion. There are typically two types of motion within the Milky Way galaxy for stars, gas, and dust. The stars in the disk of the galaxy are going on circular orbits of the galaxy, at our position taking about 250 million years to do one orbit. So we've done several dozen orbits since the galaxy formed. These orbits are undulating, like a warped, old-fashioned phonograph record left in the sun too long. So we undulate in and out of the plane of the galaxy every few tens of millions of years. Other stars do the same. These vertical motions are called z-motions. These undulating motions, as with a pendulum, are a sensitive probe of the mass of the disk of the galaxy. Stars in the bulge and the halo are not doing circular but elliptical orbits, randomly oriented, and the illusion left when they're frozen in their positions is of a spherical distribution, or nearly spherical. Many of these stars are in very high velocity orbits, and of course halo stars can plunge through the disk of our galaxy, so there are some halo stars at any given time that can be near the sun. But many halo stars are far from the sun, and most of them spend most of their orbits tens of thousands of light years away, above and below the disk of the galaxy. Near the center of the galaxy, the stars doing circular orbits in the disk and those doing elliptical orbits in the bulge have much higher densities, hundreds or even thousands of times the density of stars near the sun. Stars, even in dense regions, are so small compared to the space between them that stars essentially never collide in our galaxy or any other. To map out the motion of the disk of our galaxy, it took observations extending over thousands of light years. If we just look at the region around the sun, the nearest few hundred stars, say, over dozens of light years, and measure their motions through the Doppler shift, we'd find equal numbers of blue shifts and red shifts. In 3 dimensions, these stars are moving randomly within a small box centered on the sun. That's because you have to go to larger distances to be able to sample the large systematic motion of the huge disk of our galaxy, 100,000 light years across. The spiral arms of our galaxy, difficult to see because we're within it, but we've seen spiral arms of similar galaxies, are actually not trivial to explain. The most obvious explanation, that they're fixed features, just trailing because of the rotation, doesn't work. The galaxy has rotated dozens of times since it was formed, and if spiral arms were fixed features, they would be so tightly wrapped they'd essentially be invisible. That cannot be the explanation, because the arms are loosely wrapped and there are only several on either side. Current theory has them as transient features caused by compression of density waves. This compression, the wave traveling at a slower speed than the stars themselves in their orbit, enhances star formation. The stars that form accentuate what we see as the spiral arms, which are traced by the young hot and blue stars and the gas and dust between them, but then those stars age and diffuse out of the spiral arm region. So the traveling compression wave creates what we see as a spiral arm, while the objects within it are moving at a different speed. Our expectation of how stars should move in the disk of the galaxy is shaped by Newtonian gravity. For example, by our knowledge of the rotation of planets in the solar system. With the mass concentrated primarily in the sun, we see the orbits of the planet going according to Kepler's laws, the velocities going down as the inverse square root of the distance from the sun. If the mass of our galaxy, and the spiral disk in particular, were concentrated where we see the visual stars, most of which are near the center, or much closer to the galactic center than we are, we would expect to see a similar slowing of the rotation speeds as we move outward. In particular, by our distance from the galactic center, the rotation speed should have slowed substantially below what it was closer in, and beyond our position, it should slow further still. In fact, what was observed several decades ago, and affirmed by both optical and radio observations, is a surprising contrast with the expectation from Kepler and Newton's law. We see flat rotation curves. The rotation speed does not diminish with distance going outward beyond the Sun. In fact, if anything, it rises slightly. Not only that, it continues to rise almost to the edge of the visible galaxy. Galaxies don't have sharp edges, so beyond where we see the edge of the spiral disk, there are isolated stars, and using them as tracers or probes, we can go 2 or 3 times beyond the visible disk. Incredibly, in these outermost regions, the rotation speeds are essentially constant. The expectation from Newtonian gravity is utterly different. If the mass of a galaxy were what's represented by the visible stars, the rotation speed should be high near the center, peak, and then steadily decline as you got to the optical periphery of the galaxy. In fact, what's seen is that the rotation speed peaks, levels off, declines slightly, and then stays high to the visible edge and even beyond. This is completely impossible to understand in terms of Newtonian gravity. This striking situation was what led to the implication of dark matter. The motions of gas, stars, and dust within a galaxy are keys to understanding it. In the Milky Way, we do circular motions around the center, with a period of about 250 million years. Stars in the bulge and the halo of the galaxy are in plunging elliptical orbits, which in a frozen view present a nearly spherical distribution. The huge surprise of the last few decades was that when we mapped the rotation of the disk of our galaxy out to regions beyond the Sun's orbit, the velocity did not decline. This is completely the opposite to what would be expected according to Kepler's law, whereby once you've passed beyond where most mass is concentrated, the rotation speeds should steadily and continuously decline. Instead, the Milky Way is rotating just as fast at its periphery and even beyond as it is at our position or closer in. This singular observation had led to the idea of dark matter.